Ladies and gentlemen, Blender 5.2 LTS is finally here and it comes with a brand new simulation system for clothes and hair. Yes, you heard that right. In this video, we are going to take a look at how this new system works, starting with a simple clothes setup, then exploring some of the more advanced features like collisions, like forces, and also geometry nodes customization. So let's jump into Blender and see how this new simulation is all about. Let's go! Alright, Blender 5.2 long-term support has been released recently, and with it comes a new simulation system designed specifically for clothes and hair. In this video, we are going to take a look at how to set it up with a quick walkthrough, then dive a bit deeper to understand how it works and how you can customize it to better fit your needs. So let's get started. So let's start with a quick setup using the new clothes system. In this example, I want to add some physics to the ears, starting with this one and then the other afterwards. Of course, they're supposed to be made of wood, but you get the idea. Before adding the solver, I first need to prepare the mesh. If I show you the ear on the other side, you'll see that I already created a vertex group called ear pin. If I switch to weight paint mode, you can see that I painted some influence around the base of the ear. This creates an anchor point, so the top stays attached to the head while the lower part is free to simulate. This preparation step is really important for any kind of simulation. You almost always want to define areas you should stay fixed while the rest can move. So let me show you how to set this up on the other ear. I will create a new vertex group and call it ear pin as well. Then I will switch to edit mode, select the faces around the base of the ear and assign them to that vertex group. The setup is specific to this example, but the same principle applies to pretty much any simulation. Now if I go back to weight paint mode, you can see the transition is very sharp between the pin area and the simulated area. Instead, I want a smoother fall off, so I'll go to weights and use smooth a few times. I can increase the iteration quite a bit to create a much more natural transition rather than having a hard boundary. After that, I can do a bit of manual painting to reinforce the anchor point at the very top, making sure this section stays firmly attached during the simulation. Of course, you could also transfer the weights from one side to another, but I wanted to show you the full setup process. Finally, I will smooth those newly painted areas one last time, and that's it. We now have a proper pinning setup where the base of the ear remains fixed while the rest is free to simulate. Now that both ears are prepared, let's take a look at the quick setup for the new clothes solver. Alright, now let's focus on this left ear and set up the quick setup through the modifier. I will go back to the modifier tab and switch to solid viewport shading. In the modifier section, I'm going to add a new modifier, and this one is called under the simulation category. We are going to take a look at all the three simulation modifiers, but let's start with clothes as I mentioned earlier. So I will add this one. This modifier is actually based on geometry nodes, so later on we'll dive a bit deeper into how the system works behind the scenes. But what is really interesting is that it's much simpler to set up and use compared to previous clothes systems. Of course, it is still experimental, so you might encounter some small issues when using it, but overall the workflow is really straightforward. By default, the simulation is already running, but of course we still need to add more details and settings to avoid unwanted behavior, like for example the ear simply falling down. Right now it's technically working, but we need to define things like the pin group we created earlier and add colliders around the mesh. If I press play, you can see that the ear is falling because there is no constraint or interaction with the rest of the scene yet. It's not aware of any storaging objects. Here we have the pin group option, which should look familiar. This is where we can connect the vertex group we created earlier. If I select ear pin, this is the exact vertex group we created before, similar to how you would assign specific areas when working with the rig or skinning. Now if I restart the simulation, you can see that the ear stays attached to the head. We have the pinned area at the top and the rest of the ear is now free to simulate. We are going to adjust physics behavior and add collisions in the moment, but you can already see how much faster and more optimized this system feels compared to closed solutions. The simulation is cached directly while playing through the timeline, and the performance is really impressive. You can also invert the pin group if needed. Then we have two other important settings: stretchiness and beddiness. As the name suggests, these control how the material behaves. If I increase the stretchiness, you can see that the ear becomes much more elastic and stretches further during the simulation. On the other hand, increasing beddiness makes the simulation softer and allows the mesh to fold and react more naturally. These two settings are really useful to avoid having a simulation that feels too rigid. The right balance will depend on the type of material you're trying to simulate. Now, the next important step is adding collision objects. At the moment, the ear is not interacting with the head, so we need to tell Blender that the mesh should act as a collider. I will select the head, add a new modifier, and under simulation I will choose collider. This modifier is quite simple. We have settings like softness and friction, which control how the collision behaves with other simulated objects. We also have the margin, which is really important. It adds a small distance around the collider to prevent objects from intersecting. For example, this avoids the ear going inside the head or a close object penetrating another surface. You also have the option for deforming, which allows the collider to update if the shape of the object is changing over time. The boundary option can be useful to restrict the simulation inside the shape of the collider. This can help control where the simulation is allowed to happen. Finally, edge contact improves collision precision by taking the edge of the mesh into account for more accurate interactions. For this example, I can leave everything at default values and the collider is ready. Now I need to tell the close simulation which objects should be considered as effectors. If I go back to the ear and press play, you will notice that the head is still inert because we haven't connected it yet. This is probably the trickiest part to understand if you don't look at the documentation, but everything happens in the effector section. When using the modifier directly, you mainly work with collections. Later, when we explore the geometry node setup, we will see that you can define objects more precisely. For now, I've created a collection called effectors. The name doesn't matter, you can call it whatever you want. Inside this collection, I placed the head object with the collider modifier enabled. Back on the ear modifier, I will simply enable the collection option and select the collection containing my collider objects. Now if I press play, you can see that the ear is properly colliding with the head, which is exactly what we want. To test this further, I can animate the head. I will switch to pose mode, add a few keyframes, move forward in the timeline, rotate the head slightly, and return to the original position. Now when I run the simulation, you can see that the head animation is taken into account, the collision updates, and the ear follows naturally. Finally, say that the second ear is exactly the same process. I select the other ear, add the close simulation modifier, assign ear pin vertex group, adjust the setting if needed, and define the same effector collection containing the head collider. And now if I press play, both ears are simulating and interacting with the head, showing the full effect of the new closed system. So let's take another example to explore some of the other settings available in the close modifier. Here, I've added another base sheet along with the darts. The sheet is the object that will be simulated, so just like before, I added the close dynamics modifier to it. For the dart, I added the collider modifier and placed it inside the same effector collection we created earlier. For the collider settings, I added a bit of margin because the geometry of the end of the dart is quite thin, and this helps avoid intersection during the simulation. I also enabled edge contact to get a bit more precision, especially around the edges and contact points. On the close object itself, for now, I only specify the effector collections and left the other settings at their default values. So now, if I simply press play, you can see that we already have a simulation happening. The dart is going through the close because I added some keyframes to animate its movement. As you can see, the collider is interacting with the close, and the close simulation is running correctly. Nothing too complex here, but this example allows you to explore some of the additional settings available in the close dynamics modifier. One of the really interesting new features is the ability to tear the close during the simulation. If I enable the tear option, you can see that by default it's not really doing much. For the tearing effect to work properly, it's important to add some stretchiness to the claws. So if I increase the stretchiness and run the simulation again, you can see that now the dart is able to go through the claws and actually tear it. This is a really cool feature. I can adjust the amount of stretchiness to control how easily the claws breaks. Of course, the result will also depend on the subdivision level of your mesh. In this example, the claws is quite low resolution, which is why the tearing effect is a bit rough. But you get the idea. If I increase the stretchiness even more, you can see that the dart goes through almost instantly without much resistance. The result can look a bit unstable, with the piece moving around, but by lower values and adding some benniness, you can create a much more natural claws behavior. So keep in mind that when you are using the tearing settings, you generally want to combine them with some stretchiness to get a more visible and effective result. Next, we have the solver settings, which controls things like simulation speed and quality. Depending on the number of simulation steps and constraint steps, you can improve the accuracy of the simulation, but this can also have an impact on performance. Then we have the structure settings. Here you can control things like friction, which changes how the claws reacts when interacting with other objects. You can also adjust the mass, which is really important when you have multiple simulated objects with different weight, and they will react differently depending on their values. The collision radius is another useful setting. Increasing it can make the collision less precise, but can help improve performance, while lower value provide more accurate integrations. Finally, we have damping, which is a classic setting in physics simulations. It controls how much energy is removed from the simulation, affecting the overall stability and the way the claws react. Increasing damping can make the simulation feel heavier and more controlled, but it can also impact performance. And that's pretty much everything you need to know about the main setting available directly in the Claws Dynamics modifier. At any point, you can also add additional collider objects. For example, I can take this ball and place it inside the same effector collection. And if I press play after the dart goes through the claws will also interact with the ball. I also need to make sure the floor is properly set up as a collider. Right now it's already inside the effector collection, but you can see that the claws is slightly intersecting with it. This is where the margin setting becomes useful. If I increase the margin value slightly, for example to 0.1, and run the simulation again, you can see that the claws now respect the floor collision much better. Of course, this value is quite high for this example, so you can adjust it depending on the scale of your scene and the amount of separation you need between your object and the claws. Alright, so now let's dive a bit deeper into geometry nodes, understand what's happening under the hood, and look at some setup that can be really useful when managing this new physics system. First, I will clean up the scene a little bit. I'm going to remove the modifier from the ball and the plane and hide the dart. I will focus only on these two objects. For this example, I'm going to move the ball outside the effector collection while keeping the floor inside the collection. The goal here is to show that, when working directly with geometry node, they are not limited only to collections. We can also specify individual objects from the scene and use them as effectors. But first, let's take a look at what is happening inside the modifier itself. I will go back to the object and add the Claws Dynamics modifier again. Instead of staying in the modifier panel, I'm going to switch to geometry nodes. This is a node system that's actually driving the simulation modifier. Having access to this setup is really useful because it allows you to go deeper and customize your behavior, while still keeping the simplified modifier interface for artists who don't necessarily want to work directly with nodes. This approach is really helpful because it gives you both options: a simple setup for quick adjustments, and a more technical workflow if you need more control. One important thing to remember is to unpack the data block so you have full access to all the nodes and parameters inside the system. Looking at the node tree, you can see that the modifier is basically creating an output that is then exposed back into the modifier panel. The most important part is located at the end of the node setup, with these specific nodes. The new claws and hair physics systems are powered by this new XPBD simulation node. This is a core system responsible for everything we have been testing so far. Another important node here is the combined bundled node. The idea behind this node is that it allows us to combine multiple pieces of simulation logic together. For example, we have our main closed simulation connected with the effector inputs, which corresponds to the collection we selected earlier containing our collider objects. But the advantage of working directly in geometry nodes is that we can add additional objects independently. For example, I can add another input here and search for a collider node inside the simulation section. Then, for the geometry inputs, I can use an object info node. This allows me to manually pick a specific object from my scene and add it as an additional collider, without needing to place it inside the effector collection. So now let's select my ball, enable relative mode, and connect this geometry output into the collider input. Now, if I press play, you can see that the plane is reacting with the ball, even though the ball is not inside the effector collection. If I enable the timeline again and replay the simulation, you can see that both objects are working correctly. The ball is interacting because it has been manually added through geometry nodes, while the floor is still interacting because it is a part of effectors collection. This is where the power of geometry node setup really comes in. You can create much more advanced workflow by combining collections and individual objects together using these bundle inputs. For example, you could add multiple custom collider inputs, each controlled separately with object info nodes, and build a much more flexible simulation system depending on your needs. Right, now let's talk about something that I'm sure you will want to add to any simulation, I mean forces. Based on this geometry node setup, we are going to create a much simpler setup and add external forces to our simulation. This will allow us to go beyond just using effectors, object information, and the bundle system we explored before. So let's delete everything and go back to our plane, and I'm going to create a new geometry nodes modifier. Inside the geometry node graph, I will start by adding the closed dynamics nodes. As you can see, we recover all the settings we had in the default modifier. Expect that they are not exposed as inputs yet. At the moment, nothing is directly accessible from the geometry node interface. Later, we will expose some of these parameters so we can easily change settings and adjust things like the effectors collection directly from the modifier. If I press play right now, you can see that the close is simulating, but it's not colliding with anything. So let's start by recreating our effector setup. I will focus on the effectors inputs and add the effectors collection we've used before. Just like earlier, I will add a combined bundle node and connect it to the effector inputs. Then I will recreate the same system we built previously using a collider node and an object info node. I will set the object info node to relative modes, pick the ball, and connect everything together. Now, in addition to the object inside the effector collection, we also have our ball connected directly through geometry nodes. Now, if I press play, you can see that the ball is interacting with the close. But there is some penetration happening between the two objects. The advantage of this setup is that the collider is now completely managed through the closed object. The ball itself doesn't need any modifier. Everything is controlled from this single geometry node setup. To fix the penetration, I can simply adjust the collider node directly here. If I increase the margin value slightly, you can see that the ball now respects the surface of the close much better. Now let's add forces to the simulation. For that, I can simply add the custom force node. There are different types of forces available, and we can connect it directly into the combined bundle nodes. The main parameter we need to control is the force input, which uses vector values. We can adjust the force direction, the type of force, and the geometry space depending on the result we want. For example, if I add a negative value on the d-axis, the fall will push the close downward. This will make the simulation react faster and create more impact when interacting with the floor and the ball. I can also continue adding forces on the x and y axis to create different directions of movement. If I enable the viewport visualization, you can clearly see the effect of the force on the object and how it influences the simulation. And that's the basic setup for adding custom forces. From here, we can also expose additional settings, like stretchiness and bendiness, directly from the geometry nodes modifier. To go even further, we can create a vertex group, just like we did earlier with the dog ears. This allows us to control specific areas of the simulation. Now, here, I'm simply selecting some faces and assigning them to a new vertex group, which we can then use to define where the closed simulation should be affected. So now let's assign this vertex group here. I can now go back to weight made mode and adjust the influence a little bit. It doesn't have to be perfect for this example, I just want to quickly paint an area to demonstrate the workflow. And I can rename this group if needed, or simply leave it as it is. The important thing is that we now have this pin group exposed directly in our custom modifier. This is one of the main advantages of building this system through geometry nodes. Any parameter we decide to expose can become available directly in our own physics modifier, giving us a much cleaner and more artistic-friendly workflow. Now I can select the vertex group I just created and use it as a pin group for the simulation. So if I press play, we now have our custom close setup with everything managed through geometry nodes, the wind forces, the collision system using effectors collection, and the additional settings we exposed ourselves. This gives us a much more flexible way to build and customize our own physics tools. And lastly, let's talk about the hair system and see how quick is it to set up. I'm going to use our little character here, and you are going to see once again how simple, straightforward, and powerful this new system is. I will start by selecting the head, then I will press Shift plus A and add a new curve empty. This will create a new curve object linked to the head, with a geometry node setup already created by default. Inside the geometry node setup, we can see that we use a very similar structure to the closed system we explored earlier. We have two main parts, the animation and deformation side, which is the existing curve system, and the new simulation side using the XPBD simulation node. Just like with the closed system, we can continue customizing this setup by using things like the combined bundled nodes, adding a specific colliders, object info inputs, forces, and now let's add some hair on our little character. This should be a fun example. I will select the head and switch to sculpt mode. Then I will use the hair tools to start adding some strands, and let's create something a bit more playful. Alright, that's enough for now. I will go back to object mode. Now if I select the hair object and go back to the modifier tab, I can add some additional modifiers to adjust the look of the hair. Under the hair section, I will add a trim hair curves. This will allow me to control the length and the size of the hair, making it a bit more suitable for our little character. From here, you can continue adding different nodes and modifiers, such as blending, clumping, curling, and other curve adjustments. For example, I can add some curl to the hair to create a more stylized and funny result. Of course, I can keep experimenting with different settings and add more variation to the hairstyle. Now, to enable the actual simulation, the only thing left to do is switch the geometry node mode to simulation. I will go into the physics section, and you can see that we now have access to a very similar set of settings compared to the closed system. We can define effectors, add additional colliders through the geometry node setup using the combined bundle node, and customize the simulation behavior. If I press play now, you can see that the hair is now reacting to the environment and simulating dynamically. Of course, to get more complete results, I will simply need to add the head, ears, and other elements as colliders, just like we did before with the closed setup. And that's it! This is how quick, simple, but also deep and customizable this new physics system in Blender 5.2 can be, both for closed and hair simulations. And that's a wrap! Thanks for watching, guys! I hope you enjoyed this video. Don't hesitate to leave a like, subscribe to the channel, and I see you in 2 weeks for a new one. Ciao!